All right, so serial representation. So serial just means we're using a single electrical conductor to transmit however many bits we want to transmit. So because it's a single conductor, it's relatively inexpensive. The only problem is if you want to transmit, let's say 16 bits, well, you can only transmit one at a time. And at a time means per clock period. Clock periods, we'll get to what clock periods or what clocks are and how we use them, but serial representation is used in lots of things nowadays. Telephone lines, PCs, computer networks, pretty much everything. Some of the high-speed serial communication standards are ISDN, T1, T2, T3, USB, Ethernet. There's 10 base T and 100 base T, which are Ethernet standards. So they're kind of a subset of Ethernet. And then, of course, cable, DSL. Your COM ports on your computers can be about 115 kilobits per second, but it can be different speeds than that, but that's about maybe the average. Then, of course, USB, which is everywhere. So USB uses different speeds depending on the version, but you can typically expect it to be in the hundreds of megabits per second. So when we represent a serial, when we serially represent a number, a binary number, which the example there that they gave us, the 011011100. So they put that in a diagram at the bottom, and you'll notice there are two signals. So there's our CP signal, that's our clock signal, and I mentioned clocks. You can think of clocks like a way to mark events in an electrical device. Pretty much everything has a clock in it nowadays. If it's a digital device, it has a clock in it. Your PCs have clocks for the CPU. The CPU has its own clock. Sometimes if you have a graphics card, a GPU, it'll have its own clock. Your various chips on your motherboard have different clocks. Everything runs on clocks, though. And basically, a clock just tells devices when to update or when to change their state. Or in this case, in terms of serial communication, it tells a system how to separate bits, or when to expect the next bit, or read or write the next bit. So in this example, you can see our string of bits, which actually you'll notice that they're transmitting it in reverse. They're transmitting it with the least significant bit first. So they transmit a 0 first, and that clock, you'll notice that the bit-to-bit changes occur on the falling edge of that clock signal, meaning when the clock goes from a 1 to a 0. At that exact moment, that's when the device that's either transmitting or receiving this series of bits, that's when it knows to move on to the next bit, or that the next bit is here, or to start the next bit. So you can see it's transmitting a 0 first, then the clock ticks here, and then it transmits another 0. Then the clock ticks here, and it transmits the 1. It sets the SO line to a 1. Then the next clock ticks, it's another 1, and then a 0, 1, 1, 0. So that is how we transmit a series of bits over serial communication. The opposite of serial is parallel. Parallel uses separate conductors for each bit, so it all depends on the device, but some devices, have 8-bit parallel buses, meaning they have 8 different conductors, so they can transmit 8 bits at the same time. Some are 16 bits, but There are multiple separate conductors for each bit. It's fast. It's very fast because if you think about how long it takes to transmit 8 bits over serial, well, it takes 8 clock cycles, right? Because you have to transmit 1 bit at a time. You only have 1 conductor to transmit over, so it has to be 1 at a time. Parallel, if it's an 8-bit parallel bus, then, and by bus, I keep using that term, but basically I just mean a set of conductive lines, basically, that devices can place voltages on to represent bits. So it's just a term for the collection of conductors over which we're transmitting or receiving data. So the parallel bus can be very fast, depending on how many bits it is. If it's an 8-bit bus, you can transmit 8 bits at the same time, while as with serial, a serial connection, you'd only be able to transmit 1 bit at a time, so it would take you 8 times as long to transmit that one string of 8 bits. So, you know, when at first glance, parallel seems really nice. Why wouldn't we use parallel for everything? Because it's so much faster. Well, the problem is it's expensive, prohibitively expensive, the larger scale you get. We have parallel buses in our computers, on our motherboards, but that's because the distances between devices that are communicating over parallel is very short, relatively short. You know, you're one chip on the motherboard talking to another chip, that's a relatively short distance. So you can have parallel lines going between those devices and have it be very fast and not so expensive because it's such a small scale. But when you get to larger scales, you know, especially, you know, the reason we use serial for USB, for Ethernet, is because it's cheaper, much cheaper, particularly over long distances. And, you know, we've also improved serial communication so much through, you know, noise canceling techniques and just the way we build cables, physically build them to prevent any data loss. A bunch of factors into why we use serial so prevalently, but the main thing is that it's expensive. Our parallel is expensive. So typically you'll find parallel in smaller scales, like they know they're inside a computer. You'll have plenty of data buses, just on a motherboard. But even there are some external devices that use parallel as well. It's not so common anymore, but parallel printer interfaces like LPT1 used parallel connections. SCSI uses parallel connections, that stands for Small Computer Systems Interface. That's more of you find that more with server hardware and stuff like that. So, but it is technically a parallel transmission method. And here are just a few little tidbits about those two standards that I mentioned. LPT1 being an 8-bit parallel, around 115 kilobytes per second. And be careful, I noted at the bottom there, when you see a capital B, it's always bytes. When you see a lowercase b, it's bits. So that 115 kilobytes per second means it's sending 115,000 bytes per second. And if there are 8 bits in a byte, you just multiply that number by 8 to figure out bits per second. But then SCSI uses 16-bit parallel up to 160 megabytes per second. So, the difference between parallel and serial is basically that are we sending bits one at a time over a single wire, or are we sending many bits, or at least several bits simultaneously over separate conductors? Serial is sending it one at a time, parallel is sending it several at a time. And then we discuss those advantages and disadvantages of one over the other. Serial being very inexpensive because it's only a single line you have to transmit over, but it is technically slower because you can only send 1 bit at a time. And then parallel is the opposite. You can send many bits at a time, and it's pretty fast, but particularly the larger scale you get, the more prohibitively expensive it is and impractical to use parallel transmissions. So the last point there that they mention is more of an exercise in some calculations. They're asking how long it'll take to transmit two 8-bit binary strings, so a total of 16 bits, using both serial and parallel if the clock frequency is 25 megahertz. So they're asking how long it will take, but they give us a frequency. So we're going to have to go back to our method of calculating period based on frequency, which is our 1 over frequency formula. So they give us a frequency of 25 megahertz, so 25 million 60 hertz. So then if we go back to our calculator and we divide 1 by 25 million, we get that number. It's a 4 with 7 zeros in front of it. So we get that number. So now we just, to simplify this number and add a prefix to it, we can just move the decimal place over. We want to move it over in sets of 3 to get a nice even prefix attached to this. So we'll move it over 1, 2, 3. That would be milli. And then 4, 5, 6 would be micro. And then we'll do it one more time. 7, 8, 9. We'll have to add a 0. But 9 would be nano. So 40 nanoseconds is our clock period. They gave us the clock frequency, that's the period. So with parallel, they don't tell us how many bits the parallel transmission would be. So, we could just assume that it would be a 16-bit parallel bus. And if that's the case, then transmitting 16 bits would only take 1 clock cycle. So it would only take the 40 nanoseconds. However, serial can only transmit 1 at a time, so knowing that it can only transmit 1 bit every 40 nanoseconds, we just multiply 40 by 16. It'll take us 16 clock cycles to transmit 16 bits. So we just multiply 40 by 16, and we end up getting 640 nanoseconds total to transmit all 16 bits. Or you can think of it as 0.64 microseconds.